Hello, everyone. Welcome to today's episode of On the Edge with LF Edge. Today's topic is Fledge, how Google, OSIsoft, FLIR, and Dianomic use Fledge to implement Industrial 4.0. Just a couple of housekeeping items before we get started. Attendees will have the option to post Q&A in the chat window at the bottom. However, you will be muted. So if you have any questions throughout the session, feel free to just type them in that dialog box, and we will either type you answers back or cover them at the Q&A portion at the end of the presentation. So let's introduce our speakers. We can flip the next slide.
Sorry. Yeah.
All right. So today we've got Bill Hunt with Dianomic. He's the CTO and co-founder. We have Dan Lazaro with OSIsoft. He's a senior technical program manager of the CTO's office. And we have Mike Steyer with Google Cloud. He's an AI solutions manager. Thank you all for joining us. Without further ado, I'm going to pass it over to Bill to get us kicked off.
Hi, everyone, and thanks for showing up, and thanks to LF Edge for hosting this. So first, I want to talk a little bit about LF Edge. So the Linux Foundation is the largest open source consortium out there, and they're responsible for Linux, they're responsible for Kubernetes, and a number of other valuable projects. And they have a group called the LF Edge, the Linux Foundation Edge, which is focused on building a set of tools for the edge that are all open source. And there actually are several pieces to that. So there's a consumer edge, there's a telco edge, there's industrial edge, and so forth. And Fledge, which we're going to talk about today, is an open source stack that's defined for the industrial edge. Now, one thing about open source, so open source is probably the best way of eliminating silos, making sure that everything works with everything else, and that's why we at Dianomic gave the code to Linux Foundation. And one of the challenges with open source is you don't want to build your infrastructure around something that was built by two guys in a garage. You want to have some confidence that it's going to be there ongoing. And so, as I say, the Linux Foundation is the largest open source consortium. And also in the Linux Foundation Edge, LF Edge, there are a number of very powerful premier members. And so you can see some great logos here. So it gives you the kind of confidence that, that this is going to be around for a long time and will be widely adopted. So, and the Linux Foundation Edge, a couple takeaways about them. They're really all about making everything interoperable. So being open and harmonizing across these various communities, and they host various things such as Kubernetes and the LF networking as well. And if you'd like to learn more, you can go to lfedge.org, or there's a couple other links here for Twitter or YouTube. So with that, I'm going to pass this over to Daniel at OSIsoft. Just a quick background. So OSIsoft is the largest in their space. They're adopted at a number of different international industrial companies, most international industrial companies. And OSIsoft actually invested in Dianomic with the intention of building Fledge as an open source solution. And their CEO, Pat Kennedy, is on our board. So they've been instrumental in building Fledge on that side. And Daniel has been working with us for some time, so he's a sharp guy and a good friend. And Daniel, tell us all about that.
Thank you, Bill. So let me introduce you to OSIsoft. OSIsoft is the most trusted source of real-time operational data. We enable the collection, standardization, contextualization, and federation of large volumes of industrial operational data. We are implemented in more than 21,000 sites internationally, with over 2 billion streams and growing. We've been delivering consistent value for over 40 years, and we are continually innovating to bring new technology to operations. Data is widely acknowledged to be one of the most valuable assets in business. Data drives everything in industry and in our culture, and its use is fundamental to how companies compete nowadays. But not all data is the same. We will argue that operations data is a unique resource. The more people consume it, the more valuable it becomes. So why is this true for operations data? For companies that rely on high-value assets and processes for their core business, like manufacturing, utilities, discrete, critical industries, among others, those assets alone are not differentiating. The data is. Next, let's talk about how OSIsoft delivers extraordinary value across the industrial enterprise. Good data leads to smart decisions, as opposed to garbage in and garbage out. But what does it mean to have good operations data? In operations, this means real-time, high-fidelity data available to the right people at the right time. It's in context that you see the big picture validated by others so that it can be trusted. Good data is reliable and secure. Moreover, it includes historical records and its origins for data provenance. Good decisions that result, ideally connecting daily operations with corporate initiatives. Now let's add analytics to the mix. That includes advanced calculations and algorithms, artificial intelligence and machine learning techniques to describe, diagnose, predict, and prescribe. From this comes smart decisions and thus better outcomes. It's that integration of smart decisions into a strategy that leads to a fundamental business change in how you operate. All of this resulting in data that can be fed back into the system, creating the cycle of continuous intelligence. This shows another way that the value of data actually increases over time. So in summary, OSIsoft Pi system delivers real-time, high-fidelity operations data to people, applications, and AI/ML platforms. Data from assets, sites, and organizations rendering on any client device anywhere. In our world today, the competitive winners will be decided by who drives the best, fastest decisions on a continual basis. That can be achieved by using continuous data to power continuous intelligence, which drives continuous improvement. So why is the edge important to our customers? There is valuable data at the edge that is often stranded because it is beyond the reach of automation systems. For industrials, the edge is the boundary past which they have not instrumented their equipment or devices. At remote locations, solutions are required to handle unreliable network conditions. Some of these environments are too rough for traditional PCs. Fledge solves the diversity and complexity issues when collecting and processing data beyond the process control network. Fledge's superpower is the integration of good data, analytics, and decision tools for better outcomes at the edge. Fledge, initially seeded by OSIsoft and Dianomic, is now a diverse project within the LF and is a great example of open source integration. OSIsoft recommends that all industrial customers and partners begin their IoT journey by integrating Fledge into their industrial deployments. We ask you to join our growing community where OSIsoft and Google have already contributed to. And with that, I will pass it on to Mike, who will provide Google's perspective.
Thanks, Daniel. I'm now unmuted and appreciate the introduction. And I'm excited to talk now about how Google fits into this picture. So as Daniel said, we've started to contribute to the Fledge project. And unlike OSIsoft, Google is not necessarily a well-known name in manufacturing and industrial IoT. But in fact, we've been thinking about and working on the same problems for a very long time. And the reason for that is that the intelligent manufacturing space in industrial IoT is really built on the same digital backbone and digital infrastructure that we've been looking at in all of our consumer devices and digital analytics and our data management tools. So some of the trends that we're seeing, of course, is the need for real-time data insights, real-time activity monitoring and connectivity, applications to simulation, robotics, advanced technologies, integration of these fundamental data systems, and then really an understanding of human-machine interaction. The trends that we're seeing, just as much as OSIsoft and Dianomic have seen, and Linux Foundation, are this movement toward the Internet of Things, collecting data from the edge, development of big data tools, and of course, from our perspective, cloud computing. Machine learning is really where we can bring a significant differentiation, and I'll talk about that in a minute. And then the proliferation of devices and applications, both consumer devices, handheld mobile devices, as well as industrial manufacturing devices, is a very important trend driving this direction. To the next slide, please.
Sorry. There we go.
So for most organizations, as Daniel was describing, the foundation of this IoT initiative is collecting the devices, connecting devices to gather data and drive decisions. An important part in the middle there is generating the insights from that data. Those insights, that analysis, is really what drives those better decisions. And so where Google sits in this picture is connecting to the devices, the Fledge devices, and connecting to the OSIsoft Pi system, and bringing to bear the power of our data platform and our data infrastructure and our machine learning tools to generate insights that drive those better business decisions. So I'll talk now about the applications and the technologies that we're bringing to bear on this problem. Next slide, Bill. When we think about industrial AI at Google, we're really thinking about not just a platform, but an integrated approach to AI for industrial applications, all the way from machine data acquisition and data ingestion through our machine learning tools. So on the acquisition side, we're happy to partner with Fledge and integrate with the Fledge project to stream data from those edge devices into our cloud tools, and with OSIsoft likewise to extract data and bring data from the Pi system into our data and analytics platform. All of that is backed up by our cloud security, pervasive security applications, and then all that data can come into our AI and AutoML tools. So AutoML is an application that allows you to generate and train and optimize machine learning models on the fly without any coding on your part. So there's no need to develop a machine learning model to write TensorFlow code. The system will do that for you. It's applied to both structured data, time series data, as well as to visual and video data. There are applications for both of those to generate an automatic machine learning model optimized and using the best of breed neural network technology. As part of the platform, we also have tools for modeling, for managing and deploying AI models, and even for monitoring performance of those AI models and understanding the decisions that they make. This is a particularly important application and technology for industrial use cases because it gives you a framework for understanding the decisions that the model has made and changing the parameters of the model if the decisions that the model is making are not understandable and explainable, both for audit purposes as well as for performance improvements and optimization. So you go to the next slide, Bill. As we look at building an IoT platform based on the Google Cloud tools, there's 4 key pillars that we want to emphasize. First of all, the notion of intelligence everywhere. That's a key reason why we were partnering with Dianomic and with Fledge and with the Linux Foundation to be able to provide that AI intelligence and the models pervasively throughout your infrastructure, whether it's on the edge devices or it's in the middle using our Anthos platform or indeed up in the cloud running on our AI platform. All of those are places where we can apply and deploy an AI model. Our serverless scalability capabilities is what allows you to deploy and run applications and scale out nearly infinitely without deploying new servers, to scale up and scale down the resources that are needed to run more advanced models and train more advanced models. Security is a fundamental component of our platform. It has been since the beginning. We're taking a lot of our internal technologies and internal security optimizations and tools and approaches and making those available now to our enterprise customers, and indeed pushing those out, not just in the cloud, but pushing that technology really out to the edge devices. And then the most important part, really, especially as part of this conversation, is our strategic partnerships, the partners that we're working with to really complete the components and complete that end-to-end architecture for a full-fledged industrial IoT platform. Next slide, Bill. That's where this comes in. We can bring in our AI expertise, our state-of-the-art technology and advanced in artificial intelligence, moving from things like our optimization technology that we've worked with on DeepMind, our AutoML, automatic no-code generation of AI models. We're working to integrate that down into an end-to-end manufacturing workflow, and we can advance that technology innovation working with our AI experts on our side and the manufacturing subject matter experts that we're bringing through with our partners. So between our expertise in AI, the partner technology and services through LF Edge, through Dianomic, through OSIsoft, putting all that together, we're really ready to build an AI solution that can plug into customer data, plug into existing workloads, and deliver advanced AI technology and data management tools in this sector end to end. So I'm really excited about this, and I think there's a great future here, and happy to be part of this and work with Dianomic, LF Edge, and OSIsoft on this project. So I'll hand that back over to Bill now and say thanks very much, and Bill will take it from here.
Great, thanks a lot, Mike. And thanks a lot too for all your support. Both OSIsoft and Google have been just fantastic partners in contributing code, contributing use cases. They've been instrumental in the building of Fledge. So, so if you stand back, industrial IoT, there's a number of factors that are coming together that are making industrial IoT a thing. So you've got all these sensors that are coming online that are cheaper and smaller than ever before. Every day your storage cost and your compute cost goes down. Every day you have new tools to analyze the data. And every day everything is more and more connected. And so it's pretty obvious you put all these things together and it can really enable the transforming of industrial businesses. So there's a lot of reasons why industrial companies want IoT. They want to just collect the temperature across the plant, or wherever they want to bring data in, but they tend to have a couple major use cases. And the first is around predictive maintenance. So the idea being that you've got, if you have these very expensive assets, these multi-million-dollar machines, you want to make sure that they're always up and they're always doing good work. And so you want to be sure that when they need to be maintained, that they're maintained quickly, and that they're not maintained too often, that they're not, you don't want to replace something when it doesn't need to be replaced. So doing predictive maintenance, figuring out when they need to be maintained is very important. And then the second is making sure that they are always doing high quality work. So the components that they're being manufactured are always good quality. So ultimately, it's all about quality, efficiency, safety, and reducing environmental impact. So these are the capabilities of Fledge. So first of all, it's capable of collecting data from anywhere, from any kind of sensors or any kind of source. It can transform that data in flight. So as it's moving throughout the network, the instances of Fledge can change things from as small as changing, say, Celsius to Fahrenheit, or they can do much more complex transforms like machine learning sorts of things. They can buffer the data. So if Fledge is running in a haul truck going through a mine, or out in some cabinet that's rarely touched, and you aren't confident on the connectivity, well, Fledge can buffer the data to make sure you don't lose anything. And then Fledge has an event engine so that there's anomaly detection out at the edge. So if you have problems, you know about them immediately. And then ultimately, it's all about integrating into other systems. So it can deliver the data to one or more local or cloud destinations. So that's what a single Fledge does. You hook a sensor to it, hook the other end to a data source or data destination, and the data will just flow. But you can do more complex things. You can have multiple sensors. You can send it to multiple destinations, and you can send it from one Fledge unit to another Fledge unit. And so that way you can build these hierarchies or meshes. You can have Fledges run in a high availability mode so that if one of them, the hardware dies, that you don't lose anything. And ultimately, you can build these distributed applications that can be quite powerful. Fledge runs on Linux, so it runs on pretty much any hardware that runs Linux. There are users who have deployed it, especially on industrial gateways, are a big place where it's deployed. It can also be deployed on Raspberry Pis or Google Coral boards. So these are valuable for, you can do development with it on these inexpensive platforms and then roll it out to something that's more industrially rugged. Or you could take one of these cheaper devices and just consider it like a disposable sensor so that you put it out somewhere, and if it breaks, then you just put another one out. And Fledge is also capable of running inside Docker containers or as a virtual machine. And so it runs inside various PLCs and routers, including there's some devices here, Cisco and Moxa and Fago. And to give you a sense of how people are using Fledge, so this is in the power transmission and distribution world. This is Tenaska, actually, I'm sorry, this is Jacksonville Energy. They're the power company in Florida, in Jacksonville, Florida, and they monitor substation transformers. So they collect data from those transformers, they process it inside Fledge, running inside Cisco boxes, and then they send it to multiple destinations. They send it to OSIsoft, and they also send it via Kafka to a trouble ticketing system. And then this is Gradient Racing. They're actually, they race race cars, and they've got Fledge connected to thousands of sensors throughout the car, including cameras that are watching the track. And then they take that data and they process it locally, and they send it off to Google Cloud. This is running inside an NVIDIA server with Fledge. And in Google Cloud, they build a digital twin. So they actually build a digital replica of that race car inside Google Cloud. And then they do various optimizations so that they can then tune the car such that it's perfect for running. So the cameras watch the road and understand where various things are, what the condition of the track is, and that sort of thing. And this is actually particularly interesting to other industrial companies because a lot of the technology that is here is directly applicable to other kinds of vehicles. So if you're in a haul truck that's going through a mine, then you want to do maybe different kinds of optimizations, but you'd like to build a digital twin and optimize your whole process. In discrete manufacturing, this is General Atomics. They make military aircraft. The paint booths, the picture in the lower left, house these aircraft components, so they're quite large, and they're large enough that they get these microclimates within them. So they have multiple sensors for temperature and humidity throughout the paint booths. And the paint process is not just cosmetic; it impacts the flight characteristics of the plane if it's done wrong, and they have to hand sand it if it doesn't go well. So it's actually kind of an important part of their process. And you can see the big screen TVs with the red and yellow in that picture. Those are running applications on Fledge that give various status to the workers there. And then that data flows out to OSIsoft Pi. So this is the architecture of Fledge. Each of the green boxes is a microservice, and each of the blue boxes is a plugin. And plugins are a key part of the Fledge architecture. The idea is that there are lots of plugins that exist today. So off the shelf, you can build things to solve lots and lots of problems. But if by chance a plugin doesn't exist that you need, it's very easy to create your own. And so there's open descriptions and there's docs and sample code to build all the kinds of componentry inside here. So the way the data flows, it flows from the south service on the bottom. And there are various kinds of plugins there, such as directly connected sensors like temperature, humidity, pressure, current, all those kinds of things. But there also are a number of industrial protocols like OPC UA, Modbus, MQTT. If you're in the industrial space, these are very common protocols. So the data flows through the south service, through the storage layer where it's buffered, and then out the north service to its eventual destination, to Pi or Google Cloud or Kafka or Splunk or to another Fledge device. And then along the way, you can apply filters which transform the data, and those filters can be applied in ingress in the south service or at egress on the north service. And they can transform the data in any number of ways, including, like I say, just simple transforms of Celsius to Fahrenheit, or there are some others that I'll talk about more around vibration processing, or you can even have machine learning models that are applied in these filters. The event engine in the upper left watches the data as it's flowing through, and it registers for data of interest, and then it runs various rules against them. And the rules can, again, be as simple as if the temperature goes over 150 degrees, I want to take some kind of action, to much more complex. They can be autoencoder ML rules, for example, or much fancier math rules. And then if a rule triggers, then an action is taken. And the most typical action is to create data to send to some other system to notify the other system that something's gone wrong. But you can also do things like run an external app. So Fledge lives on these gateways, and so you can run other applications on the gateway such that you could turn off a machine, or you could flash a light or something like that, or you could notify a human directly that some anomaly has occurred. The orchestrator in the left watches the whole system. It has various self-healing capabilities. So if it sees any challenges, it attempts to repair them. And it's also responsible for all the scheduling and backup and user management and security and so forth. The whole system is accessible, is configurable and monitorable by a GUI. And the GUI comes with it. And then the GUI actually leverages REST API. So you can use the GUI, but also you can send things directly to the REST API. So it's very easy to tie into your existing infrastructure or write scripts to access it. So vibration data and high-speed data is actually a special type of data that's more and more industrial users are interested in. And it's a little different than other kinds of IoT data because it's very high volume and because it's not necessarily intuitive what it means. So if you look at the graph on the left, it's pretty obvious what it means if that's a temperature graph. So you can say yesterday it was cold, today it's hot. If it gets too hot, I want to take some kind of action. But on the right, you really don't know what that means. You get a graph of vibration, and it's just you can't tell if the machine is working well, not working well, or any kind of knowledge about the state of it. And then you come back to the left, and you can be collecting data at a sample a second, maybe even a sample a minute, and have a good handle on what's going on in your world. But on the right, in vibration data, by definition, it has to be many samples a second, even thousands, tens of thousands, even millions of samples a second. So now you have this data that's very voluminous, but it's not clear what it means. So what do you do with that problem? So the first thing is that Fledge has some built-in filters, some transform plugins that can make that data more useful, more operational. So the first is on the left. There's a root mean squared. And what it does is it tells you the energy of a wave. So you end up with it, rather than the vibration data on the last slide, you end up with something that looks like like this on the left. And so that normally you just use that to tell what speed the engine is going at or the device is spinning at. But if you keep a baseline, you can also use it to do predictive analytics, because if bearings are starting to wear, then they'll require more energy. And so that means that the RMS value will be different. And so you can use that as the most basic of predictive analytics tools. But typically you'll want to do a deeper analysis. And so there's also an FFT, a fast Fourier transform plugin, that can break a waveform into its component waveforms. And then there are various other capabilities that Fledge has on top of that FFT. So it can tell you the top peaks. It can tell you what the main shaft, if the main shaft speed is, and the harmonics across it, and a number of other valuables. Fledge can also do conditional forwarding, and the idea here is that if you have vibration data, it can flow into the buffer inside Fledge. So Fledge just continually collects that data, but it doesn't send that data forward. And then if you detect an anomaly, then it will send not only the data forward in the future, but it'll also send past data forward. So it can send the last 5 minutes of data or 30 minutes of data to, so that way you have the best of both worlds. You aren't continually flooding your network with this vibration data, but when you really need it, you have the diagnostic data that you really need. And this anomaly detection is really critical to this flow. So the idea is you want to detect when there's a problem. Well, how do you know when there's a problem? And so that's where machine learning becomes such an important consideration. So inside Fledge, we really think of machine learning in two different ways. The first is as intelligent sensors, so where you can point a camera at a welding machine and determine the quality of the weld, or you could watch the vibration, as I mentioned, or you could point a camera at an area where there shouldn't be any people, and if it sees any faces, then it can notify someone. So that's on the south side, and as the data comes in. And then also you can do machine learning in the rules engine. And so that way you've got, that's where anomaly detection happens. And you can do various techniques to watch the data and determine if a machine that you're watching is healthy or not. The ML engine that we use inside Fledge is Google's TensorFlow, which is the most popular ML engine in the world. And it also happens to be open source. And so TensorFlow has a version called TensorFlow Lite that's specifically designed for the edge. So you can run these ML models out at the edge. And also Google makes some specialized hardware for ML acceleration called TPUs. And Fledge can also leverage those so that you have high performance ML out at the edge. This is a typical classification pipeline that various real users are using. I won't go into all the math, but the basics are that the raw vibration data comes in, it gets broken down into small segments, 1/5 of a second each. Each of those time slices is divided up into frequency bands. And then for each of those time sliced frequency bands, we calculate a number of what we call features. And those features, for example, you might take the median of that particular box, or the mean, or the standard deviation, or the number of times that 0 is crossed, the number of times that means is crossed, the number of the kurtosis. There are a number of different features. And each of those 30 features across each of those frequency bands, you can think of like a fingerprint. And so, or the sum of all those, or the aggregate of all those is like a fingerprint. And then you can feed that into a machine learning model and ultimately classify whether in this particular case, whether a bearing is bad or whether cavitation has occurred, that sort of thing. There's also FLIR has been a great partner, and they've also contributed code to Fledge. And FLIR is the largest infrared camera company in the world. And with FLIR cameras, you can point the camera at shop floor and draw bounding boxes around particular machines, or you could point it in a smaller area at a single machine and draw bounding boxes around areas of interest on that machine. And then FLIR will report back the minimum, maximum, and average temperature for each of those bounding boxes. And so that then Fledge can process that data and pull it in and leverage it. And then also lastly, as I say, we're with Dianomic. And so if you have a lot of Fledges, one of the things that we do for commercial support of that is that we provide a way to manage these at scale. So we have a central configuration tool called Fogman, and it can do auto discovery. If you put new Fledges out there, it can find them and bring them into its management. It has templating, so if everything is scalable. It has a focus on the machines that are being monitored, so you can have screens that show you the status of those machines. It's very secure from the device to the destination. And in addition to doing the configuration, it monitors the devices and the data, and it can be hosted or it can be on-prem. And with that, I'm going to turn it over to Ashwin, who is going to demo actually that same pipeline I showed you before. And what we're going to do in this demo is we're going to collect high-speed vibration data. We're going to process it using Google TensorFlow, and we're going to detect when there are anomalies and then deliver that enriched data to OSIsoft. Take it away, Ashwin.
Hi, everyone. So this is our vibration demo. I'm Ashwin Gopalakrishnan from Dianomic Systems. And what we're running here is a vibration demo in which we have this motor setup. It's basically a tabletop setup of a motor. It's representative of something that you might see in an industrial setting where they have pumps and so forth and other pieces of rotating machinery that they want to monitor. Now, this particular motor is currently engaged with one of two bearings. This is a good bearing that's engaged. And what I have here is a bad bearing, one that is known to have an inner race fault, common problem in these type of settings. Now, on top of the motor, we have an accelerometer attached to measure vibration. And that accelerometer is connected to a gateway in which Fledge is running. Now, moving on to this screen, this is OSI's Pi software in which, as far as the data flow goes, we're collecting data from that accelerometer into Fledge, processing that data, and then sending data out to OSIsoft's Pi, hosted on my laptop here, and visualizing that data within. Within the Fledge system, we're collecting raw high-frequency data at 8 kilohertz and processing that data at the edge to provide both RMS, or root mean square analysis, as well as fast Fourier transform analysis and sending that data forward. We're visualizing the data of RMS here above, And we're also periodically sending the raw waveform data from Fledge into Pi. So as not to completely saturate the system with high frequency vibration data at 8,000 hertz. In this case, every 1 minute or so, we're sending about 5-6 seconds of high frequency vibration data into the Pi system, even though we're continuously collecting within Fledge at all times. Now, in addition to these two filters, or processing at the edge plugins, we also have a third filter, one that uses a neural network model to identify if a good bearing or bad bearing is running. In this case, when a bad bearing is detected, we will send raw vibration data to be analyzed into this error stream. Right now, the good bearing is running. So what I'm going to do is turn off the motor and exchange the good bearing for the bad bearing that's on the desk. Again, this bad bearing is known to have an inner race fault. Tighten this screw to engage the bearing to the motor. And if you can hear the difference, there's an audible difference that happens when we engage the bad bearing. One thing that people do automatically when, as far as time series goes, this entire stretch over here is where we've been collecting good bearing data. This point here is where we were running to exchange the bearing. And this is the bad bearing data. Now you can notice that immediately once the bad bearing was running, that neural network model identified that a bad bearing was running and sent up raw vibration data to be analyzed to this separate stream. This is aside from the periodic sending of raw vibration data that is happening here. Now, 2 points of measure, people may use just the RMS or FFT analysis to identify, a good versus bad bearing and be able to see what's happening there. But people can also dive into the raw vibration data to see the exact waveform that's produced and compare it against the good bearing data. Now on the fog lamp side here, what's essentially is happening, this is our fog lamp GUI. Again, on the south side where we're collecting data, we're getting data in at 8,000 hertz and run it against the 3 filters, one for RMS, the second for FFT, and third for bearing health, which is the neural network model that identifies if a good or bad bearing is running. On the north side, data flowing out from Pi, of course, we're sending data to Pi here. And we're also using our notification engine that allows alarming and notifications to one, periodically send 5 seconds of raw vibration data forward, regardless of good or bad state, as well as one to send error into the error or data into the error stream when a error is detected by the neural network model. Okay, and that's essentially what we have for the vibration demo.
Great, thanks, Ashram. Actually, we had a couple of questions around hardware. Do you want to show the, if it's convenient where you're at, do you want to show the table with the hardware stuff on it? Maybe walk
Sure.
through?
Give me 1 second. Okay. This is just a desktop just filled with different hardware that we either acquire data from or that we run on itself. So Fledge, it runs on industrial gateways such as this. So on the left, there are a few from Advantech. In the middle, a Dell gateway, as well as on top of that, a Moxa Class 1 Div 2 gateway, as well as on the right-hand side, Nexcom gateways, one in which the Google TPU is built in as with a TPU processor as a PCI Express based setup. and on the bottom, a gateway that would run in automotive pieces, collecting J1939 or CAN bus data. Fledge can run within any general purpose Linux system, such as Ubuntu or Debian-based Linux, Red Hat Enterprise Linux, or CentOS, and across platforms like ARM 32 or 64 or Intel setups. So here we have something like the Raspberry Pi 4. In this case, this is the Google Corral piece, which is an ARM 64 piece. These various gateways are either Intel or ARM based. This piece here is a microcontroller in which just one of the services, in this case the South service, was spun out. And here we have a Wago PLC, which is able to run FogLamp as a Docker container within the PLC itself. On the left-hand side here, we have different data acquisition modules that we're using to collect data. This is a typical industrial setup where you would have something like a data acquisition module collecting 4 to 20 milliamp current loop and information or analog device information, and bringing that into a data acquisition module, and then using a protocol such as Modbus to collect that information into Fledge using our Modbus plugin. We have other industrial plugins like OPC-UA, for example. Nexcom has contributed the J1939 protocol as well to the Fledge repositories. And so here is a typical panel setup that you may see. It would include a gateway on the top left or top right, perhaps a high frequency data acquisition module seen on the bottom right, or perhaps just a simple data acquisition module seen on the bottom left, as well as a power supply, all on DIN rails within a panel that you would typically see, waterproof and sealed tight with conduit. And here is an example of a high frequency data acquisition module that we would ingest data from. The accelerometer here would connect up to a data acquisition module. This is a 4-channel data acquisition module with tachometer input as well. And so as to guarantee that the sampling rate is held steady across a single master clock, and so that you could do your analysis in a synchronized way. Other points of hardware to show are the FLIR infrared camera. This is the FLIR AX8 camera. A current transducer that is also seen in industrial setups to measure the current consumption of a particular motor, perhaps, as that is indicative of performance and wear as well. And so those are basically the hardware pieces that I'd like to show you. Any questions?
Great, thanks, Ashwin. I'll tell you what, how about, so I've been watching the chat window, and there seem to be several questions across how this was trained. So maybe I can spend a second talking about that. Let's see, let me share my screen again. So let me, I'll first walk you through, got some other slides here. So this shows FogLamp in this slide, which is our proprietary version, but the code is identical to Fledge. So everything that you see here is very relevant to Fledge. So the first, if you think about an industrial ML project, there's a few stages to it. So the first of it is that you have to get data. And so Fledge is actually an ideal thing for collecting data, right? Perhaps you already have data, but perhaps you just don't know. And in fact, this is a typical thing when we engage with actual users, is that they'll have some machine that has some challenge and they want to solve it. But the first problem is, well, they've got to get the data from the machine. Well, since Fledge is all about collecting all kinds of data, that just makes it perfect. So you can deploy one or more Fledges out there and hook up sensors to them. And now you've got that data goes out to whatever cloud you're going to use. Google is a particularly excellent one for doing your ML training. And so the first thing, of course, is that the South plugins allow you to collect any kind of data into Fledge. And then also, if you choose to have lots of them, you can use our FogMan product to work with them in a distributed fashion. But that's not mandatory. You also can use the rules that are built into Fledge. to collect only the data that's needed. So perhaps you collect lots of data, but you on the edge decide how much of it you want to use for training data. And perhaps you want to do some pre-processing on that data. So you do that. Then the next thing is out in your cloud, out in Google, you build the appropriate models. And you send those models back down, and then you can build filters and rules or use existing filters and rules inside Fledge, and you distribute those models out to those Fledges. And finally, you can use Fledge to send your intelligent data to wherever it needs to go. And you can use those filters or those rules and those North plugins, whether you're sending that data to Pi or whether you're sending it to somewhere else. And so that's the typical process. And let me walk through, a couple people asked questions about like, how did we actually do what Ashwin just showed? So I don't want to spend tremendous time on this, but I'm happy via email to talk to anybody in any detail we want. But what happened was the raw vibration data came in. This is, well, actually, I'll start with how it actually worked in the demo, and then I'll walk back to how it was trained. So there's raw vibration data came in. It was broken into 200 millisecond segments, and each of those 200 millisecond segments was broken up into frequency bands using what's called wavelet packet transform. And so for each of those 200 millisecond segments, each one of those frequency bands, a series of features was calculated across each of those buckets, and approximately 30 of them. And so, for example, there's one feature is the median of it. One is the mean, the standard deviation, the number of times the graph crossed the zero, the number of times it crossed the mean, the kurtosis. There's just a whole bunch of these. And so you can think of that all those features times all those frequency slices is a fingerprint of that 200 millisecond segment of time. And then that's basically fed into a model, and then the model comes out and it says good or bad. And actually, that particular model that Ashwin has also can classify beyond good or bad. It can identify if it's there's different types of bearing faults. If the inner race is faulty, or the outer race, or the bearing itself, or cage, or so it can identify different types. And the way it's trained, actually, let me start off by saying that the model that Ashwin showed is a neural net model, but we have others that we've done as well. One of them is an autoencoder that's a specialized kind of neural net that kind of collapses to the center, if that makes sense, and effectively encodes what normal looks like. And then it's used to determine, well, is this normal info we're seeing or not? And then we also have one that's a XGBoost tree, if you're into the weeds of these sorts of things. And the way it was trained was basically taking the exact opposite path. So, or actually the path is the same, but instead of doing a machine learning, or instead of using machine learning model, we trained a machine learning model. So we walked it through the same pipeline of going into the 200 millisecond segment, going through the wavelet packet transform, calculating the features, and then the data was labeled manually. So basically the humans, namely Ashwin, noted which time segments were good bearing and which time segments were bad bearing. And then we also trained it with various types of, there's various tunings on that machine where you can set there's a knob you may have seen Ashwin turn. And so we recorded that as well. And then we trained the model to look for those sorts of things. I hope that makes sense. Let's see. There also was question about, does it run on NVIDIA? And in fact, Mike answered in the chat window that in fact the gradient racing team is running it on Jetson Xavier, and hopefully Ashwin's show and tell of some of the pieces that we've been, or the gateways we've been deployed on, shows you some of the types of hardware that we did there. Let's see, what should we answer next? Jill, should I walk through these, or how should we?
Yeah, so we've got just about 8 minutes left. So, and it looks like we've got about 4 questions in the Q&A window. So why don't we just start taking some of those and get as much done as we can in the next few minutes. And if you want to talk about the TSC calls as well. Sure,
absolutely. Let's see. So the first question says, what kind of edge application can be managed by fog lamp? For instance, can it be used to update AI/ML models running on an edge TPU? Well, you can kind of think of FogLamp or Fledge is the edge application. And so, in our typical use case, it is actually leveraging the TPU. So the TPU is a specialized processor, like a CPU, but it's it's a TensorFlow processing unit. So so you can actually Fledge is designed to be a kind of an application platform where you build your applications on top of it. That said, it can work with external things, and in fact, one of the things that is typically done, there's our events engine will when it detects an anomaly, it can take a number of actions. It can create data, so another system can take action on it, or it can email people, or it can run it can interact with an external application that's running on the same gateway. So you could have a second application that's, say, running inside a container that it could interact with. And so in any way that you can interact with those, Fledge can do that. Let's see, are available plugins to connect to Siemens PLC and Siemens drives. So we have an S7 connector or a plugin, and we can certainly, we'd love to, I've got our email at the end there. It's info@dianomic.com, or I'm bill@dianomic.com. Feel free to reach out and we can talk more about that. Let's see, where's the ML model being generated? Always on the gateway. Actually, this is an important consideration. So the way this works is that the models themselves are not being generated in FogLamp itself. They're being generated outside in Google Cloud. And so the idea is that there's kind of a distribution of responsibilities. So Fledge is excellent at collecting the data. In some cases, it's excellent at labeling that data, right? If you're collecting, say, you've got a ball bearing stamping machine, and then you've got another machine that takes that ball bearing and puts it into a subassembly, and then maybe you've got some process where you QA those things. Well, we can collect all that data, and then you can then use that as the labels. And in some cases, you just may know what the label is. Now, in some cases you don't, and in that case, there's a manual labeling process that would have to happen. And then once you've got that labeled data, you bring it back into Google Cloud, and then you can generate the models, and those models are put out on the gateways, and then that's where they take action. Can the ML model also be generated on the gateway itself? So coming back to the last, so technically it can, but the reality is that for most of the kinds of things that you want to do, it's too computationally expensive, especially if you want to be doing it on a regular basis. If you want to, if you're playing with Fledge, if you just want to install it and do things, there's things you can do there on it itself, but that's not really its design. Its design is to be the collection and then later the execution with those. Execution engine with those models. The AI was in Python or C++. So what Ashwin just showed, everything was done in Python on the Fledge side, and however, all the plugins can either be Python or C++, and C++ is higher performance. So Python is very prevalent in the ML world, of course, and so you can certainly do everything in Python. But there may be cases where you want to do it in C++, where you later want to port what you've got to C++ to make it faster. Although that said, what Ashwin showed you was real. That was processing, I think it's 8K samples per second of data, and it handles that just fine. So the performance, it depends on how many sensors you want to be bringing in, and how fast you want to be bringing data, where you start to think about performance things.
Yeah, just to chime in, the plugin for the data acquisition was done in C++, so was the RMS and FFT, but the ML filter to produce good or bad bearing health analysis was done in Python. So it's for this demo, it's a mixture of all of those.
Yes, and then a question about the various classes of machine defects. So we've got literally 2 minutes, so I won't go into another technical deep dive, but in this demo that we have, there's actually 2 things that are running in parallel. One of them is detecting if there's an anomaly, and the other is constantly watching out for classes of machine defects. And so today, that demo really only detects inner race faults and outer race faults in this demo. but in fact, you can train it on anything that's, that you'd like. And in fact, that's typically the goal is, and it depends on the type of machinery. We're working with some folks who have a centrifuge in the food processing worlds where they're looking to optimize that whole process. And so there it's a specialized type of classification that they're looking for. But at any rate, wherever you can get labeled data, you can build models. What about the performance penalty when doing additional data processing on the edge? Well, let's just say that one of the goals that we're really trying to achieve here is to do fancy things out on the edge. There's times where you really can't do your processing in the center of your network, especially when the data is just too voluminous. And so as much performance as can be done is what we do. It's like I say, the demo that you just saw was all real, and there's other things out in the field that are real. So every project is a little bit different because every bit of data is a little different, every model is a little different. But we do the best we can to make sure it's high performance, and we can talk more detail about how to manage that and how to evaluate that if you'd like.
Yeah, so I think we're about to get cut off. So I'd like to thank all of our speakers today and all of our attendees. The webinar will be available to watch on demand within the next few days. And if there are more questions, you all are welcome to join TSC calls regularly for the Fledge project.
Yeah, and let me, am I sharing my screen? Let me at least show you real quick the links that we have here. As Jill said, the TSC info is here. That's our monthly meeting around Fledge, where that's the technical steering committee. So you're welcome to show up and interact, of course. And also, if you'd like to evaluate Fledge, you can find the documentation here and the code here, and a number of other things around us too, wiki, Slack, mailing list, that sort of thing. And then, like I say, if you'd like to just directly reach out, you can reach us at info@dianomic.com, or I'm bill@dianomic.com. We'd love to hear from you.
All right, great. Thanks so much, everyone. Have a good day. We'll see you next time.
Thanks, everyone. Appreciate your time.